Today I will talk about the entanglement of statistical physics or statistical mechanics. Why do I want to talk about the statistical mechanics? Because by now it's a very well established theory and very successful. Statistical mechanics evolves from the classical statistical mechanics to quantum statistical mechanics, and it is as good as ever. In any case, if you look at the introduction of the book of Feynman on statistical mechanics, he wrote that the statistical mechanics is just like climbing up the hill and going down on the other side. Climbing up the hill is trying to deduce the basic principle of statistical mechanics till you get up to the canonical distribution or equipartition, something like that. Then when you find all these results, then you apply all these results for specific problems, and most of the work of course is to apply all these results in everyday problem and go and compute the tremendous number of systems, and everything works perfectly. But the point is the first part, when you just try to deduce the principle. This is not slightly well established. If you look in many different books, they all reach the same results. Even in classical textbooks, you can see they all reach the same point, the canonical distribution, and then the mechanism is same. But how to get that is not very well established. So let me see what the problem is. When you first encounter the statistical mechanics, then all the story you see is very natural. You have to talk about a system, like you can say about a cup of coffee which has a very large number of particles. So then you realize that you cannot know about everything, about what is happening there, that there are simply too many particles. Or also you can say one cup of coffee behaves much like another cup of coffee. So although you most probably did not prepare the same thing for the two different cups, it does not really matters as far as you're concerned. Your concern is what everything is hot or not. You are concerned only with the properties of the particles. So, or whether you like it, independent of the details of all those particles. So what the great paradox of statistical mechanics is? The great paradox is that the subjective lack of knowledge, that you don't know what the situation is, apparently has objective implications. So let's see how it works. Starting from a macro state, a big description that what is going on. You give just the basic number, say the number n, roughly the number of particles. Let we have 200 milliliter of coffee with its pressure and temperature. Then there are many microstates that are compatible with these macroscopic parameters, pressure and temperature, and you count the numbers of the microstates that are compatible with macroscopic conditions, and you get number n. Then you do the simple thing, you just take the logarithm of n and call it as entropy. Since the entropy depends upon energy, so you take the derivative and suddenly you find that the way in which the number of microscopic states, that is how much you know about the system, changes, has objective things either too hot or too cold. It means this formula gives the correct value of temperature. So put your finger into the coffee. It's very objective that your finger is burnt or not. And that has to do with the way in which the number of microstates, and how much I don't know whether the coffee hot or not. So that is the paradox. So somehow definitely it works because it gives the correct temperature. But why does it work? That is something that people has struggled to make it precise. There are a lot of different solutions available, but here we discuss two. One of them is the Gibbs ensemble and is to talk about the ensemble average. So he considered that we do not have one cup of coffee, but you have many cups of coffee, and all of them are prepared according to, say, microscopic parameters. But the microscopic things are not under your control, and then you have to take an average over the state, which is wonderful as formal tool. But the reality is we do not have a large number of cups of coffee. But well, what other possibility is there? That is time average. That is, you look at 1 cup of coffee, but 1 cup of coffee now and 1 second later have more or less same macroscopic parameters. Suppose it does not so quickly cool, but the microstate changed. So in fact, waiting some time, I prepared different microscopic states that are all compatible with macroscopic state. So then the idea is that of making an ensemble average over different cups of coffee, I could take only one and just wait time, and that will create many. So now both of these approaches are problematic in their own ways. So to solve these problems, suppose you have a very large number, take the spin of this case, and there is nothing else but is just a closed system composed of these n spins, and suppose that they are in pure state. It means you know everything about the system as a whole. Then the entropy of the system is zero and will stay zero all the times. It's a pure state. No matter how it evolves, it always remains a pure state. And I have the complete knowledge about the system. But some of the spins that at beginning they all start with in a direct product state, say up. Then in particular, not only do I know everything about all the spins, I also know the state of these spins of the interest. But as time goes, if there is any interaction of these spins, these spins may get entangled with the rest. So now, if I just ask myself, what is the state of subsystem? I don't know, but no one knows about this because it has been entangled with all the rest of states. So quantum mechanics offers the possibility of having the objective lack of knowledge, although you know everything about the whole universe. And perhaps this may give you a way to define all these quantities like entropy and temperature and pressure and so on in any objective way. Then they will no longer be paradox. While do they have objective implications? Now, suppose the system being the whole universe represented by a Hilbert space H, and impose some restrictions capital R, and then divide the system into two parts, a subsystem and a Hilbert space of the environment. I mean, a cup of coffee is a subsystem and the air molecules are environment, being the rest of all. And in general, these restrictions are quite specific. Now, what is the postulate of equal a priori probabilities? All you know that the state of the universe is in Hilbert space R. Because you don't know anything more, you have to take all possible states in HR with equal probability. You have to think, since you don't have any knowledge of the system, that the state of the whole universe is identity based density matrix in HR. So the density matrix of the universe is identity, and its dimensions are therefore normalization, because the trace of the density matrix must be. And now I define the state of the subsystem, which is simply the trace of the identity matrix over everything, trace over environment, and when you trace it over the environment, you are left with some density matrix for your subsystem, and this is called canonical state of the system, omega s. This omega s is produced by the subjective lack of knowledge. And to solve that subjective lack of knowledge, let a pure state phi of the universe. Now I want to compute what is the state of subsystem in this particular pure state of the universe. I have to trace the density matrix corresponding to the pure state phi of the universe and trace the environment out and left with some density matrix rho of the subsystem. It means the state of the system when the universe is in the equiprobable state ER. We can interpret this principle as principle of apparently equal a priori probability. For almost every pure state of the system, the state of sufficiently small subsystem is approximately the same as if the universe were in the equal probable state ER. In other words, almost every pure state of the universe is locally indistinguishable from ER. For almost all the states phi of the subsystem, that is almost canonical. Therefore, density matrix of the subsystem is almost canonical. That is for every pure state which belongs to the Hilbert space in the restriction R of the universe. So the system is in canonical distribution regardless of where that particular pure state of the universe is. So this generalization incorporates the grand canonical case as well as the standard canonical case and will lead to many other interesting insights. For example, it may be useful in situations where usual weak interaction approximation does not hold. We want to look at the density matrix of subsystem rho and look what is the distance between that subsystem and the canonical state omega s, and we measure that this distance is smaller than a number which is ds over de effective whole square root, where ds is the dimension of Hilbert space of the small subsystem and de is the dimension of Hilbert space of the environment given the restriction R. When the system has fewer number of particles than the environment, the dimension of Hilbert space is exponentially small than the dimension of Hilbert space of the environment. Because, for example, if you have a system of n spins, so you have n spins and you look at the subsystem K of the environment, dE is equal to k power n minus k, and of the system subsystem ds which is equal to 2 k power n, where if k is much smaller than n, then the difference between these two numbers is exponential. This tells us that the difference or the average distance between the state of the subsystem, the actual state when the universe is pure, and the canonical state is exponentially small, because as small as the system, more and more the particles, which is the limit of statistical physics. Since everything is continuous, so then let us take the volume of the Hilbert space, which is such that the distance between the actual state of the system and canonical state of the system is larger than some value epsilon. Then what would we expect? The larger the distance, the smaller the number of states. So most of the states will not be at larger distance, and the volume is likely to be. The important thing is the dr, which is the dimension of restricted Hilbert space. When the dimension of Hilbert space increases, this value here decreases exponentially. So it tells that the volume of the state that are far from the canonical state is exponentially small. In fact, it is double exponentially small, because DRE is the dimension of a restricted Hilbert space. Now take some arbitrary point there, an arbitrary state represented by psi. It is such that if you look what is associated with the density matrix rho s of a subsystem will be the trace of psi to psi and will approximately be the canonical state. And also there will be some tiny volume in which the states are not like that. These are the states that are not yet in equilibrium, but this tiny volume here is double exponential small versus the whole universe. So what we have learned is the main thing, that we don't need the subjective lack of knowledge. That is, I don't need to consider that I don't know where the state is and to average over this entire Hilbert space HR. Every single point behaves like the average over everything, so we can conclude that postulate of equal a priori probability is misleading, and we can make it correct by saying principle of apparently equal a priori probabilities. That is, although the state is a pure state, as far as the subsystem is concerned, it behaves as if I would have taken average over the rest. The statements are purely kinematics. That is, I did not say anything about the Hamiltonian, about how it evolves, about how it happens. I also did not say anything about what the restriction is. So let me here put some remarks, and one of the basic problems of the statistical mechanics is to find what the canonical state is. How does it look? So to find out what is omega s, this is the very first remark. When you take some specific conditions, like you fix the energy of the system, you fix the temperature, you presume that there are no long range interactions, so that you can isolate more or less the subsystems which does not interact with the rest of the universe. In that case, the omega s becomes the exponential h over k beta t, which is the Boltzmannian, and it is well known what sort of approximations and assumptions you need to do. Now we don't have anything to say about what is omega s, what is the canonical state. In fact, we just have omega s that depends on the restrictions that we put. The second thing is that I'm not bound to the usual restrictions, that is to usual way of setting the microscopic parameters. This is all about the distance between the pure state and average, and holds for whatever the restriction I would like to put. And I don't need to say anything about the spectrum of the Hamiltonian, whether the densities of the states in the environment is dense or not. And Hamiltonian is purely the property of a large Hilbert space, and in large Hilbert spaces you have something that is similar to the large number of ordinary classical theory, and one of the main mathematical tools for that is the Lewis lemma. According to Lewis lemma, suppose you have a function f that is defined on a sphere in d-dimensional sphere. Hilbert space is a sphere because every pure state is normalized 1. Now we have an arbitrary point in the sphere. You have to start from the average of the function on the sphere. If you select an arbitrary point p at random, the probability of the distance between the actual value of the function and the average is exponentially small. But the most important is, which is a maximum value of the gradient. If the function changes very rapidly, it can very quickly gets from validity differ from the average. But once I can fix the rate of change, almost every other point is very close to the average as the dimension of the sphere increases. But as we increase the dimension, almost all the points are next to the equator. In fact, every equator is very next to another equator because all of them are put over there. Also, the value of function is like the average and average like the value of the equator. So the last point is the average entanglement over the larger Hilbert space is directly what is required to derive all the properties of the statistical mechanics.